Look at Earth from a distance, and human biology makes perfect sense. Every bone, muscle, and breath we take is calibrated for this exact environment. Our anatomy is tuned to a 365-day orbital cycle, 1 g of surface gravity, and a perfectly balanced, oxygen-rich atmosphere. Yet, staying perfectly comfortable has never been our style. We possess a deep psychological drive to push past our boundaries, to explore, and eventually to expand into the stars. The problem is that the moment we leave our atmosphere, we enter an intensely hostile void. The universe outside our planet is violently cold, bathed in radiation, and incompatible with the fragile bodies we developed back on Earth. Earth is a beautiful biological cradle, but our ambition is simply too vast to remain confined to a single planet forever. To bridge the gap between our bodies and the void, we spend billions of dollars on mechanical protection. We build pressurized spacesuits, reinforced metal habitats, and heavy domes to keep our terrestrial biology intact. We know this strategy works for short durations. The Apollo moon landings proved we could survive off-world by carrying a tiny bubble of Earth's atmosphere with us. However, mechanical systems are extrinsic. They require a constant supply of refined materials and external energy to remain functional. Over millions of years, the maintenance of artificial environments becomes an unsustainable burden, as even the strongest alloys degrade under cosmic radiation. Long-term cosmic survival relies on a self-replicating adaptive system, DNA. Biological evolution rewrites the organism to fit the environment, removing the need for an external life support system. To truly settle the stars, we must accept that the humans of the distant future will no longer look like Earthlings. The outward journey begins at Venus. If we attempt to settle here, we immediately face a crushing atmosphere composed of supercritical gas. The toxic carbon dioxide and sulfuric acid create a surface pressure so intense it would immediately flatten a standard human frame. To survive the weight of the Venusian clouds, humans would evolve compact, dense frames, growing significantly shorter and thinner to withstand the pressure pushing in from all sides. We would also need to develop integrated biological filtration systems to process the toxic air. Moving further inward to Mercury offers no relief. This is a barren, cratered rock completely stripped of an atmosphere, where temperatures boil at 430 degrees Celsius during the day and plunge to -180 degrees at night. A human living here would need the microscopic resilience of a tardigrade. We'd need the biological capability to enter a hardened, dormant state at night, and quickly thaw out to repair ourselves when the sun rises. These inner planets act as cosmic forges, forcing life to compress, harden, and radically re-engineer its own chemistry just to withstand the harsh physics of the inner solar system. Mars is our most viable first colony, but it presents its own biological hurdles. The planet has a gravity field only 1/3 as strong as Earth's, and a thin atmosphere that fails to block solar radiation. Without Earth's heavy pull, Martian humans would grow significantly taller, though bone density and muscle mass would thin out. To survive brutal winters and constant radiation, they would likely grow a thick layer of fur and adopt a rich orange skin hue. Pushing past the asteroid belt brings us to Jupiter's icy moon Europa. Europa is a frozen water world with almost no solid ground. Survival here forces humanity to completely abandon land-dwelling anatomy. To navigate the subglacial oceans, future humans would evolve webbed, elongated limbs for efficient swimming, developing thick thermal protection to insulate against the cold, and gills to process oxygen directly from the water. Establishing footholds in the middle solar system requires the sacrifice of our familiar shape, trading it for height, fur, and aquatic fluidity. When we jump light years away to alien biomes, the evolutionary outcomes diverge further from our terrestrial origins. On the gas giant Epsilon Eridani b, humans would have to navigate chaotic, swirling temperature zones without ever touching solid ground. Settlers would likely evolve internal flight mechanisms to move through the thick gases. To regulate body heat through those violent atmospheric layers, they would develop color-shifting chameleon skin that adapts its tone to the shifting temperatures. In contrast, super-Earths like Kepler 452b subject life to immense gravitational pulls and heavy radiation from red dwarf stars. Humans on these worlds would be short and stocky, possessing powerful muscle structures to counteract the gravity. Their skin would grow thick and pale to lock in moisture and resist the constant bombardment of radiation. In the most alien environments, human biology proves its capacity to rewrite its own physical laws, stretching from the mechanics of flight to hyper-dense strength. Looking at the galaxy from a distance, it becomes clear that millions of years of migration will end our existence as a single homogeneous species. We will be a vast family of diverse silhouettes. The tall, orange-furred inhabitants of Mars will share a lineage with the stocky survivors of super-Earths, the webbed swimmers of Europa, and the soaring color shifters of the gas giants. The universe remains a constant, unyielding force. Our survival is found in our capacity to change, adapt, and beautifully bend until we fit into its most alien corners.